Welcome everyone to geometry. We want to continue taking a look at section 10 today, picking up where we left off in our last video. In our last video, we finished with a distance postulate, which said that between any 2 points, there's a non-negative number, or for every pair of points, there is a non-negative number that can be assigned to the pair, which is called the distance between the points. And we want to talk a little bit more about that. There was a comment that depending on how you define distance, now you end up with different flavors of geometry. And we can look at that a little bit more specifically here in Axiom 4, the ruler postulate. So let's consider the ruler postulate. For any line L, there is a one-to-one correspondence between the points of L and the numbers of the real line, such that if points A and B on line L correspond to numbers X and Y on the real line, respectively, then distance from A to B is equal to the difference in the absolute value of the difference in X and Y. Now, I want to emphasize here the type of one-to-one correspondence. Well, I suppose first of all, what I should do here is make sure we're all familiar and remember what we mean by one-to-one correspondence. So when I say a one-to-one correspondence, what I mean is that the function is 1 to 1 and onto. Okay, so 1 to 1 and onto. Okay, and then there are a lot of different functions that we could choose. For us to end up in Euclidean geometry, we would want this to be a linear function. A linear function is going to give us that if we take 2 points that are this distance away in our plane, or what we want to be some fixed distance away, no matter where we're at along our line in our geometry, then when we take that, that's going to correspond to 2 points on the real line that are also the same distance apart. Okay, so we want to understand that. So we would want it to be a linear function. Of course, y equals mx plus b. If we just talk about real numbers to real numbers, this is a one-to-one correspondence. But there are also one-to-one correspondences, real numbers to real numbers, such as the logarithm function. But there's also a one. Yes, you are right. It's not a one-to-one correspondence. This only takes inputs which are larger than 0, but that does afford for us the ability to talk about a logarithmic type function, because it's 1 to 1. So it's 1 to 1 and onto if you're talking about the positive real numbers to all real numbers. And then we could also look at y equals e to the x, the exponential function. So if we take 2 y values which are 1 apart, okay, 2 different y values that are 1 apart, they're not necessarily the same distance apart in x. Okay, whereas if for a linear function, we would have that. So this is essentially what gives us a Euclidean geometry. And the others give us things that are not Euclidean, things that are not a linear relationship. So we want to know that this one-to-one correspondence, or it's helpful, a good piece of information. I suppose it's not necessary for us to know that it's a linear relationship, a linear correspondence. All right, so this axiom gives us several things. One of the things that it does for us, it allows us to recognize that the distance from A to B, of course, is exactly the same as the distance from B to A, because absolute value. Awesome. And then also, let's see here, we have that the distance from A to B is 0 if and only if A and B are the same point. Okay, so that's excellent. So when we choose a formula, when we say, all right, for a line L, there is this particular one-to-one correspondence, what we do is we use essentially the same one-to-one correspondence for all lines. If we use the same one-to-one correspondence, then our measurements of distance are the same no matter which line we're considering. Okay, if we take 2 points that are 3 units apart and then consider 2 different points on some other line which are 3 units apart, then they're still 3 units apart, right? If we use a different one-to-one correspondence for each line, then we would end up with different distances depending on which lines we're looking at, which is a little bit ambiguous anyway, because we can't consider 2 of the same points, can't consider the same 2 points on 2 different lines. But essentially what I'm saying here is, understanding that it's a linear relationship, we need to use the same m in each case, the same slope. And then if you want to take it a step further, you could say, well, all right, we're going to measure in inches, and that would require one particular m value, or we're going to measure in centimeters, that might utilize a different n value. So you can use a different m value as long as you're right, or the m value doesn't matter, as long as you're using the same m value in each conversation of the plane. All right. So this axiom will be used quite a bit. In particular, what it allows us to consider is if we have a point P on some line L with some particular distance in mind, then it allows us to say that there is exactly one point, right? Once we choose a direction, there's exactly one point that is a particular distance away. So if I want to talk about the point that's d, a length d or distance d away from P, once I choose a direction, there is exactly one of them. Okay, there's one point Q with a distance d away from P. So we're going to use that quite frequently. All right, so our next definition that we want to look at is a definition that we would likely think that we're quite familiar with, but we actually have, right, trying to remember that we're forgetting everything that we know. We want to build up our definitions from the limited collection of axioms and definitions that we already have. My apologies if you can hear my son. He's just having a great time eating some dinner right now. So, all right, so between. Right, we all know what between means, but we can be quite formal about this now with the definitions that we have on hand. So suppose A, B, and C lie on a line L and correspond to the numbers A, B, C, real numbers, right? Correspond to the real numbers A, B, and C. Then we say that B is between A and C if and only if A is less than B is less than C, or C is less than B is less than A. It only takes one of those situations for us to say that B is between A and B. Or sorry, that B is between A and C. And the notation for this is we could say that A dash B dash C tells us that A is between, sorry, that B is between A and C. And it doesn't matter which of these situations we have, they both give us that B is between A and C. But we could also write this as C, B, A. Okay, so I'm not saying that either one of these corresponds to the other specifically. What I'm saying is once we have one of these, once we have A is less than B is less than C, then we could write either one of these representations. Okay, excellent. So each line is a copy of the real number line, which gives us that for 3 distinct collinear points, exactly one of them lies between the other two. And we know that it's true simply because it's true for the real line, right? If I have 3 numbers, 7, 6, 42, exactly one of them lies between the other two. 7 lies between 6 and 42. And that's always going to be the case, right? Anytime we have 3 numbers. So since it's true for the real number line, it's going to be true on a line. All right, so our next definition is a line segment. Given 2 distinct points A and B, the line segment AB is the set consisting of, remember, a line is a set of points. So we haven't given a nice formal definition to line. What we're going to do is we're going to build up. We actually give the definition for a line segment, and then we take a look at the definition for a ray. This section does not talk about the definition for a line segment. I suspect that might actually be in the exercises. I did not take a look. So for 2 distinct points A and B, the line segment AB is the line consisting of the point A, the point B, and all points between A and B. Now it'd be nice to write that in set builder notation. So we can write that as A, B, the line segment. Notice I don't have any arrows here, right? It's just a line segment. And I have a line because it's not the distance AB. So this is equal to the point A, the point B, union with, so A and B, and all of the points P in the plane, all the points P in the plane, such that P is between A and B. Excellent. So A and B are called the endpoints of the line segment. And again, the length of the segment, right, segment, the length of the segment is the number AB. And 2 line segments AB and CD are congruent if and only if the distance AB is equal to the distance CD. And we denote this by AB is congruent to CD. We want to make sure that we are perfectly clear on the notation that's being used. So AB with a line over it represents a line segment. AB with nothing over top of it represents a number. It is the distance between the points A and B. So 2 numbers can be equal to each other. 2 line segments can be congruent to one another. So a line segment can be congruent to a line segment, and a number can be equal to a number. A line segment cannot be equal to a line segment. That's not the appropriate relationship there. So this is not right. And a distance is not congruent to another distance, right? It's equal to. So we would not use congruent to describe equivalent distances. So we want to make sure that we have that understanding. Make sure that you're using the correct notation. You will lose points for using incorrect notation. All right, just a heads up. So congruence is the word that's used to describe sameness in geometry. So when we talk about figures, we can say that 2 geometric figures are congruent, right? They're equivalent to one another. and this would mean that they have the same size and the same shape. So we've talked a little bit before in Math 220. So here they say 324, it should be 220. And maybe you've seen this in 321 as well, that we're talking about a congruence relation here. Okay, or an equivalence relation, I'm sorry, which if you were in the 321 with me in the past, those are used almost interchangeably, congruence relation and equivalence relation. So anyway, equivalence relation is what we want to be thinking of there. There is some information in the appendix of this text, it looks like, if you'd like to take a little bit more of a look at that. And of course, since congruence relation is, or a congruence is an equivalence relation, it is reflexive, symmetric, and transitive, the three conditions required for a relation to be an equivalence relation. All right, so we're going to take a look at a theorem, and we will actually prove it in this case. However, this one is going to require a prose proof, so it's not a two-column proof, it is a prose proof. So it's essentially some text, right? We're going to explain what's going on. A prose proof. So our theorem is the segment addition theorem. If A, B, and C are points such that B is between A and C, then the distance from A to B plus the distance from B to C is equal to the distance from A to C. If we look at a line here, right, if we have A, B, and C, of course, this distance plus this distance would be that distance. And that makes sense to us, right? Because we're on a line. That's no problem. But we want to make sure that we understand that completely through a proof. All right, we want to justify it. We want to be able to say, this is why we know it's true. All right, so first, assume that B is between A and C. Right, because if A, B, and C are points such that B is between, then. So we assume the if part, and then we want to show the then part. So assume that A, B, and C, or sorry, that assume that B is between A and C. So A, B, and C are collinear. Then A, B, and C correspond to some real numbers A, B, and C, right? Lowercase here. So this is, we talked about this a little bit before. We get this, the ruler theorem, which tells us, or the ruler postulate, that tells us that we have a one-to-one function that gives us distance. And so these points correspond to elements in the real line. Okay, so we have these, and we actually get from that the distance from A to B is the distance between A and B. Excellent. The distance from the points, from the point B to the point C, is the absolute value of the difference in values from B to C, right? The distance from B to C. And the distance from point A to point C is equal to the distance from real number A to real number C. So we're taking the distance in the plane and we're reducing it to distances that we're familiar with. All right. Also, since B is between A and C, we have one of two situations. either A is less than B is less than C, or C is less than A, sorry, C is less than B is less than A. And in either case, we would have that the absolute value of A minus B plus the absolute value of B minus C is equal to the absolute value of A minus C, which tells us that the distance from A to B plus the distance from B to C is exactly the distance from A to C, which is what we wanted to show. Yay! Okay, so there's maybe not all of the blanks filled in here. You would want to be able to understand, you want to be able to show that the sum of these two numbers is that number. That would be a good idea. In which case you would just have to utilize the relationship here. All right, so given any two distinct points, A and B, the ray, okay, so we've talked about line segment, we're going to build up to ray now. Given two distinct points, A and B, the ray A to B is the set of points consisting of the line segment AB and all points P such that B is between A and P. Excellent. We can write that in set builder notation. Here, notice that my arrow above is pretty sloppy. It looks kind of more like a fish hook, which is okay. Really not quite ideal, so let me do a little bit better job here. But it is also appropriate to do this. Okay, so instead of having a full arrow, having the half arrow is quite all right. That's not a problem. So this is equal to the line segment from A to B along with all of the points P such that P gives B between A and B. So B is between A and B. Excellent. And that's all that we wanted to take a look at for this video. In the next section, we'll take a look at a couple more theorems, a few more definitions, and for these two additional theorems, we'll actually write these as two column proofs. So there'll be really nice examples for what we're expecting to see in the homework. Thank you for your time. I'll see you guys again shortly.